Okay, this part of the course we want to do a calculus review, a vector calculus review. Um, the first thing that we want to look at is if we have a function of multiple variables. So in this case we have some function w. It's a function of x, y, and z, but then x itself is a function of u and v, y is a function of u and v, and z is a function of u and v. So this is where we start talking about partial derivatives, which are derivatives of a function with respect to one variable only. So if we want to know how w varies with respect to u, we would take the partial derivative of w with respect to u. And in order to do that, we have to employ the chain rule because w is explicitly a function of x, y, and z. So we would take the partial of w with respect to x, and then the partial of x with respect to u, and so on. So the partial of w with respect to v, we would do the same thing, except in this case, we're taking the partial of x, y, and z with respect to v. So this is known as the chain rule, and it's pretty commonly used in a lot of applications. There are certainly some special cases. This would be a two-variable case where you have a function of x and y, with x and y each being functions of u and v. And so here's how we would calculate the partials of w with respect to u and v. It's also very common to have x, y, and z functions of time. So in that case, if you're taking the partial of w with respect to time, then you would employ the chain rule for x, y, and z with these time derivatives present for x, y, and z. You can also have that in 2 dimensions or even in 1 dimension, where some function w would depend on x, but x depends on time. So that's, once again, the employment of the chain rule. So I want to talk about some physical components that involve derivatives and scalar and vector fields. So the first thing I want to talk about is a gradient, and we want to talk about the gradient is taken on a scalar function. Here's the definition of the gradient. I'm sure most of you have seen this before. We have some scalar function f, which varies in x, y, and z. And so the gradient basically involves taking the partial of f with respect to x, partial of f with respect to y, and the partial of f with respect to z. And then each of these in their corresponding x, y, z unit vector directions. So physically, the gradient tends to represent rates of change of a scalar field. So one thing in electrical engineering that would be an example where a gradient can be employed is if you have an electric potential and there's some directional variation in the electric potential. Electric potential is a scalar, and so if we take the gradient of the electric potential, we basically will end up with the electric field, which is directional. The differential operator, which we always refer to as the grad or gradient operator, I've never heard anyone use this terminology mentioned in your book, is basically represented by partial with respect to x, unit vector I, partial with respect to y, unit vector j, partial with respect to z, unit vector k. So this is a common notation, and it's used throughout vector calculus. Sometimes it's useful to define a directional derivative. This gives an indication of the rate of change of a scalar field in a given direction. That can be done by basically taking the gradient and then finding the dot product of the gradient with a unit vector. The unit vector represents the direction of interest. So one possible example of this might be if you had a scalar potential field and you had some orientation of a geometry that involved, say, electrodes, and you wanted to know the variation or the electric field between the electrodes. That could be done by taking a directional derivative, defining a coordinate system around the electrodes if you knew the functional variation of the electric potential. So directional derivatives sometimes can give us rates of change in directions that don't necessarily coordinate with the coordinate system x, y, and z. So they can be useful. Now, the use of the gradient can also be employed to determine the direction of maximum increase. So if you have a scalar function and you take its gradient, then basically the direction of that gradient vector gives you the direction of maximum increase at a given point. So that can be useful, particularly if you're trying to do certain minimization kinds of things or looking at maximum rates of change in given directions. The gradient also taken at a particular point along a surface, then if you do that, you get basically the result is the normal to the surface. So we have some expression in x, y, and z that actually defines a surface or a curve. That happens when some function of x, y, and z is equal to a constant. That's going to represent some surface in space. So if we then take the gradient of f and evaluate that at a given point P, that's going to give us the direction of that. It's going to be a normal vector to the surface. That can be useful because sometimes you're interested in things like, determining where the normal vector lies and how that then is oriented with respect to things like electric potentials. The electric potential tends to form, sometimes you're interested in surfaces of constant potential. If you know the surface of a constant potential, for example, you can take an electrode of a given shape and put a voltage on it. That forms a surface of constant potential. So then if you want to know the electric field at the surface of that, the electric field directed away from the surface of the electrode, you can find that by employing the gradient function along a surface or an equation that defines the surface. The divergence of a vector field. So divergence is it's basically a derivative taken on a vector. So if I have some vector function v and I take its divergence, I'm taking the partial of v with respect to x plus the partial of v with respect to y plus the partial of v with respect to z. And here's just an example algebraically of how the divergence is done. The best way to physically visualize divergence is to think in terms of flows or field lines. So if I have, let's say, we'll use the example of an electric field. If I have an electric field and I take the divergence of that field, what I'm looking at is I'm looking at the rate of change of the value of the field in the direction of the field. So divergence measures rate of change along the orientation of the field lines. So if a field is exclusively pointing in the x direction, then obviously you're looking at how the electric field changes along the x direction. So another way to denote divergence is to denote it as a dot product between the gradient operator and the field vector. So here's my operator, here's my vector, and so taking the dot product, I get the same expression that you saw on the previous page. So so we always take the divergence on a vector. It does represent a rate of change of a vector field. And then we say that the divergence is a scalar function and its values depend only on the point in space. So they're independent of the coordinate system. So you can take the divergence in other coordinates and you'll get the same number. So another kind of interesting thought is this vector field V, what if that were the gradient of some scalar field, which is in fact exactly what an electric field is. Electric field is the gradient of a potential. So if that's the case, then if you take the divergence of this vector, you're actually taking the divergence of the gradient of a scalar. And if you do that, you can show that that's basically equal to the sum of the partial derivatives in each direction. And this expression is often referred to as del squared of f, or the Laplacian. It's the divergence of the gradient. So that's kind of an interesting application, because in electromagnetic fields we work a lot with the Laplacian because it can be related directly to charge distribution. So we work with the Laplacian of the potential. The curl of a vector field is basically the cross product of the gradient operator and a vector, and it can be found by evaluating this determinant shown here, where we have unit vectors I hat, j hat, k hat, and then we have partial with respect to x, partial with respect to y, and partial with respect to z, and then our vector components v1, v2, and v3. And so remember, v1, v2, and v3 themselves are functions of x, y, and z. So when we take the curl, if we evaluate that matrix, that determinant, we get the following expression. And we're assuming here we have a right-handed coordinate system. And you can just ignore this statement about if the coordinate system is left-handed, because we don't work with left-handed coordinate systems. So the curl represents rotation in the field. So this is really hard to visualize when you think about electromagnetic fields. It's maybe easier to visualize when you think about water flow. So if you think about the standard like water flow problem, where you have maybe a creek or a river that's flowing, you have a general direction of flow, but then within the flow you probably also have little eddies and little vortices that occur. So if you could think about turbulent flow. So if you look at that and you go along the direction of flow and you look at, say, the rate of change of the velocity along the direction of flow, you're looking at a divergence. If you look at the eddy currents, or the rotation in the flow, you're looking at the curl. So a curl is always visualized by something wrapping around something else. So if you have a rotation and you take your right hand and you move your fingers in the direction of the rotation, the curl is in the direction your thumb is pointing. So it's like a perpendicular vector, and there's rotation of whatever you're talking about wrapping around. So the classic example in electromagnetics is the relationship between the magnetic field and the current. If you have current flow, there are magnetic field lines that wrap around the current flow. If you have a magnetic field, there are current density flows that wrap around the magnetic field. So current and magnetic field are related by the curl, just like electric field and voltage are related by the divergence. The difference, by the way, is that magnetic fields don't contain monopoles, so magnetic field lines always have to close in upon each other, while electric fields do contain monopoles, which allows this divergence relationship to exist. So gradient fields are irrotational. So what this means is, once you've taken the gradient of a scalar, if you then try to take its curl, the curl is equal to 0. Why is that? Because the gradient is in the direction of maximum change, and once you've taken the gradient, you've taken out the rotation in the field. So there is no rotation, so the curl is 0, because remember, the gradient is a derivative. Furthermore, once you've taken the curl, you're looking only at rotation, and your divergence will be 0. So the curl is perpendicular to direction of flow. Divergence is in the direction of flow. So once the curl is taken, you're perpendicular to the direction of flow, so your divergence naturally will be 0. So that's just a couple of interesting theorems that come out of this. We also use the same theory of invariance for the curl, that the curl is a vector. It has length and direction that are independent of the choice of the coordinate system in space. So the curl will not be affected by the choice of coordinate system. The next lecture we'll talk about integral vector calculus.